All right, this is our third video for Unit 1. We're going to call this one Mass versus Volume. So first of all, let's get a definition for mass. It's just simply the amount of matter in an object. We measure mass in grams. We could use kilograms for large objects or milligrams for really small objects. Two objects have the ability to have the same size and volume but have different masses. And really there's two ways that can happen. The first way is within the packing of the atoms. So if we had two objects roughly the same size, that's my box that I'm showing there, and I had atoms inside of those two objects. Object A had atoms spaced apart like so, and object B had those atoms much closer together, then object B would have more mass. So B's mass would be greater than A if this is B and this is A. So that's one way that two objects of the same size could have different masses if those atoms are packed a little bit closer together. And yet, typically that's done by changing a temperature or the pressure of the sample itself. Now there's one other way that we could do this. Let's see if we can erase A there. Let's say that the packing of the atoms is identical from object A to object B. The difference now, though, is that we actually have maybe two different elements inside of the box. And so the element B atoms are much larger. We might have exactly the same amount of atoms in A and B, but since the atoms in B are so much larger, then the mass of B is once again greater than A. And just think about this. I mean, if you had like, I don't know, a piece of carbon, so graphite from your pencil lead, you just had a larger piece of graphite or coal maybe, which is also carbon, and then you had a piece of iron which was exactly the same size. The piece of iron would be more massive than the piece of coal just because of the size of those iron atoms. They're just larger. They're about 4 times as large. So the packing of atoms and the sizes of atoms, two ways that we can have something with the same size but a different mass. Volume. Volume's a bit different. The amount of space an object takes up. Obviously, you've talked about this in math class a little bit. In regular shapes, we can find their volume. We usually use an equation like for a cube, it's length times width times height. For a cylinder, it's the height of the cylinder times pi r squared. We always want to make sure that our measurements are in the same units. So if you're measuring your height in centimeters, you'd also want to measure your radius in centimeters. But sometimes shapes are not regular, like the human body, for instance, is not a regular shape. So if we wanted to find the volume of the human body, we'd have to do something a little bit different. And to do this, we use liquid displacement. You did this in the last lab 1 number 3, when you placed the cylinders inside of the graduated cylinder and you saw the liquid level rise. Now notice I say liquid displacement, because one of the main things about this particular process is that the object itself must sink. The entire object has got to be under the liquid. Sometimes water is a poor choice for this because some objects do not sink in water. Whoever had the maple or the wood in the last lab probably noticed this. So you might want to use a different liquid, something that's got a lower density that allows the object to sink. So we find the difference in liquid levels, and that then becomes the volume. When we're measuring volume, we use units, usually either milliliters or centimeters cubed. And it's really interesting to note that 1 mil equals 1 centimeter cubed. So you can use those units interchangeably. They're equivalent, so you usually don't even have to set up a dimensional analysis problem. So if I were asking you, hey, I've got 355 milliliters of liquid, how many centimeters cubed is that? Well, it's 355, same. It's a nice property to understand. Now, why would we have two different kind of crazy units for volume? Well, the milliliters is usually used for liquids. Centimeters cubed, that one's usually used for gases and solids. Okay, gases and solids. You might say, well, solids, that makes sense because, if I've got a cube, or a rectangular prism, whatever it is, length times width times height, that's going to come in centimeters cubed. But why gases? Well, gases fit the container that they're in. They expand to fit the container. So if the gases are in a solid container, the volume of the gas will be equal to the volume of that container, minus the thickness of the sides. So what about a relationship between these two things? Well, a constant temperatures and pressures. So if you hold the temperature equal and the pressure equal, you don't vary that. If a substance gains volume, So if you make it larger, it's going to gain mass as well. The only way for it to gain volume is for you to put more stuff inside of it if the temperature and the pressure are the same. And this is going to happen linearly. And what I mean by that is that as one goes up, let's say we put mass here on the y-axis and volume here on the x-axis. As one increases, the other will as well. So if you have no mass, you should also have no volume. So I put a dot right there at 0, 0. But as the mass increases, so too should the volume. And that's an interesting property because what we can do then is draw a linear best fit line on a graph if we're graphing mass and volume. And what we should see is that the dots that we plot on that graph kind of hit hit the line every single time. If we can draw a best fit line, then we can use a little bit of our algebra knowledge to create a equation for that line, because every line has an equation to it. And if you remember from your algebra course, the equation for a line follows the same look. It's y equals mx plus b. And just to redefine these things, m is called the slope. Okay, m is called the slope. So if I got my blue line there, if I had a purple line too, the blue line would have a higher slope. It'd have a greater number. B is called the y-intercept. Okay, now for this case, the y-intercept, as you can see right here, that should be 0. That's where your line passes through the y-axis. And remember, this is the y-axis right here. Okay, so if my line were coming like this, the y-intercept would be way up there. Now for your lab, hopefully you have two graphs that have the y-intercept passing very close to that 0 point. Okay, so let's say I know the exact equation for my line, and Google Sheets does do that for us. And let's say it comes out to y equals 2.5x plus 0, because my y-intercept happens to be 0. Well, that just means that 2.5 right there, remember, that's the slope. That equals my slope. And remember what I said about that. The slope is going to be a really important point. If you remember, slope equals rise over run. Okay, rise over run. All right, so if you look, what's our rise? Our rise is our mass, and our run is our volume. Okay, our rise is our mass, and our run is our volume. So I'm going to clear this for a second. So right now we know slope equals rise over run. And we said our rise is mass, and our run is volume. And the greater the slope, we call that, we say that the object has a higher density. So this is actually our definition for density. So if you know your slope, you know your density because it equals it. All right. So when you find your slope, like I said in that last one, it was like 2.5x in my example, plus 0. Okay. This is your slope. It'd be that's your slope. That's also your density. It'd be 2.5, and then you'd have to tag that with appropriate units, grams per milliliter or grams per centimeter cubed. Okay, so graphing this relationship will reveal the object's density, which is the main point of our materials lab, our lab 1, number 3. All right, that's the end of this lecture.